Good day everyone, I am Frederic Salimi. This e-course will be uploaded in our training workspace. If you are interested in full access of this e-course, please send us an email given in description. Have a good day and talk to you later. A brief description about my qualification and experience. I have a master's degree in dependability, which covers safety, reliability, maintainability, and availability. I also have a BS degree in process control and instrumentation. I worked several years with engineering companies like Technip and operators like Total. I was involved in pre-project, FEED, detailed design, construction, and operation. Today we discuss about hazardous area classification. This is a generic version and will be customized for your project or for your installation later. This course takes 1 day and we give you access to EPC 365 training monitor for discussion. The objective of this course is to give a practical understanding of hazardous area classification for oil and gas installations. I added to this e-course a video by Summit Electric Supply, which explains very well about the explosive limits, auto ignition and flashpoint, explosive group, IEC classifications, temperature classifications, method of protection, and electrical device marking. Electrical device marking is something like this, which should show what is a type of electrical equipment in this area. I also will explain about the purpose of the hazardous classification. If there is a building inside of the classification area, the requirement for the airlock and the requirement of pressurization of the building. Code and standards, there are several code and standards, depends on the project, IP15 or API 500 or 505, IEC 679, different parts, and NFPA 497. The purpose of hazardous area classification is to reduce to an acceptable level of probability of coincidence of flammable atmosphere and an electrical ignition source by means of segregation or by requiring electrical equipment to be manufactured in such a way to ensure it does not constitute an ignition source. Ignition control is achieved by identifying a source of the release and its likely frequency or grade, considering the flash point and physical properties of the release, the expected durations of the release, and prevailing ventilation. Hazardous zone ranking, we normally 3 grades of the release are defined in terms of their frequency and duration. First is continuous grade release. This is a release which is continuous or expected to occur for long periods. Normally it is the cumulative duration of the release exceeds 1000 hours per year. Example is condensate storage tank. Primary grade release is a release which can be expected to occur periodically or occasionally during normal operation. The cumulative duration of release is in the range of 10 to 1000 hours per year. Examples are drains and flammable liquid sample points, condensate tank vent, process and instrument vent, sumps and basins in oily water treatment, peak receivers and launchers door and vent. And finally, secondary grade of the release is a release which is not expected to occur in normal operation, and if it does,
is likely to do so only infrequently and for short period. The cumulative duration of the release is less than 10 hours per year. Examples are valves, flanges, pumps, compressors, and exhaust. Definitions of the zone. Normally, each item of equipment shall be tabulated with hazardous area subdivided into 3 zones, zone 0, zone 1, and zone 2. Zone 0 covers the part of hazardous area in which a flammable atmosphere is continuously present or present for a long period. Zone 1 covers that part of hazardous area in which a flammable atmosphere is likely to occur in normal operation. And Zone 2 covers that part of hazardous area in which a flammable atmosphere is not likely to occur in normal operation, and if it occurs, will exist for a short period. An area that cannot be affected by a flammable atmosphere or release of hydrocarbon that could form a flammable mist or a spray on release shall be considered non-hazardous. Now we discuss about classification of petroleum fluids. The fluid LPG is class 0, class 1 all the hydrocarbon with here is flash point is less than 21 degree, and class 2 and class 3A is it depends if the temperature at which the fluid is handled, TH, if it is less than flash point or it is greater than flash point, etc. These are definitions which is based on the IP code part 15. Fluid categories are typically written here. Category A is any flammable liquid that on release would vaporize rapidly or substantially, including LPG and lighter flammable liquid, example LNG. Unstabilized crude oil should be put in category B, and stabilized crude oil should be put in category C. So the relationship between the fluid classification and fluid categories is here are the classes, and these are the description about the flash point, which range, and the fluid category here, as you see here, is defined as per code and standards. Now I'll show you a hazardous area classification schedule. Normally each project we have to prepare this schedule. We have to clearly identify for the with tag number all the equipment from equipment list, that their phase, if they are gas, liquid, their molecular weight, if the fluid is heavier than air or lighter than air, and that will affect about design of the installation, about process condition, operating temperature, and maximum operating pressure, flash point, we can get this flash point, boiling point, fluid category, and density, auto ignition, and explosive limit, LFL and UFL, which is very well described at the end of this e-course by another company, and also the area, if it is ventilated or not ventilated. You have to be careful for offshore installation. You have to do CFT modeling, and if it is not well ventilated, maybe you classify as zone 1 instead of zone 2. And so the source of the release here, for example, valve flanges, and it is grade 2, and also the zone that it creates And Air 1 and Air 2 is based on these figures. If the height is more than 1 meter or less than Air 1 plus 1 meter is like this. And if it is less than 1 meter becomes like that, and if it is greater than Air 1 plus 1 it is like this. We have to clearly define this, and this will help for hazardous area classification drawing. And here is a gas group 2A. For example, this is hydrocarbon. If it was for example hydrogen sulfide, it became 2B. And finally, the maximum temperature class is T3. That means we can see it from here, auto ignition, and that we have to be careful. The maximum temperature of the equipment should not exceed 200 degrees. So here, after hazardous area classification schedule, we have to have hazardous area layout drawing. Basically, here the contractor should define where are the zone. For example, here in the middle here is zone 1, here is zone 2, and here 2A means it is hydrocarbon and maximum temperature class is T3. So it should be very clearly shown in the drawing, and we know where are the source of the releases of hydrocarbon. For example, here we know that it is a source of release here, and if we want to put the fire and gas detectors, it should be around this area. Here is GTG, and as you see here, it is a safe area. It is a technical building. It can be control room or whatever. Here it is in safe area. But you have to be very careful, as I said, in fire zone and restricted area. If the restricted area goes through this area, that means if there is a source of release here, the gas can go here. So here the air intake should be a 2 out of 3 gas detector. In case of detections of the gas and releases here, they have to close the dampers. And if there is a doors around here, it should have an airlock. So you have to be very careful about, even if you should not say that, okay, so the hazardous area is on here are safe. You have to look at the restricted area and the LEL, how far goes in case of the release in your process area. Another point that I wanted to mention, there are certain projects. If you see here, it is written, because normally here, when you put electrical equipment in this area, it should be it should not be ATEX. It is in safe area. But there are certain projects, for example, like this one, that it says regardless of location, all external electrical equipment shall be as a minimum suitable for operating in hazardous area zone 2, class 2M means hydrocarbon, and temperature class T3. The same thing for external instrumentation instrument equipment. So if you see here instrument equipment, normally we put a text. If, for example, you put some here a flame detector, it is in safe area. Since it has to work in the emergency situation, in case of the gas cloud or something happening there, there should be normally instrumentation, fire and gas instrumentation equipment should be ATEX in the process area. But this project, because of the maintainability and uniformity, they ask that all the equipment should be for zone suitable for zone 2. This is also the same for the offshore installation. For having something consistent assistant for the maintenance, and for maintenance people, they put everything in zone 2. So this is the whole thing. So you have to have the hazardous area classification for the installation, for selection of the equipment, your electrical equipment, to reduce source of ignition. At the end of this this training, you will see the type of electrical equipment that can be present in different zone. Also, the objective of the hazardous area classification is to put an airlock if we have a door in the restricted area, and also to put a gas detector in an intake to stop the dampers or stop HVAC in case of the gas ingress in this area. Now I show you how to have access to EPC 365 training workspace. Just click on safety engineering training and then hazardous area classification. Now, for the customized training, a client can put all the information about hazardous area in this directory, and then we create an e-course. And when the e-course was prepared, we give it for the company for approval, and when it is approved, we put it on the hazardous area classification for discussion, and all employee has the chance to ask the question, and our expert will give answers to their questions. Thank you for your attention. If you have any question, please send us an email to pmc@epc365.com. We have two websites. One is in French and one is in English. Both of them, they have a request form. You can send us an email. We get back to you as soon as possible. Have a good day, and talk to you in our next workshop.
The learning objectives for this training module are combustion fundamentals, fire and explosive requirements, explosive limits, auto ignition and flashpoints, explosive groups, IEC classifications, temperature classifications, methods of protection, and electrical device markings. A combustible gas or dust explosion may exist in a variety of industries, including petrochemical and refining, food processing, pharmaceuticals, and fossil fuel power generation. The vast majority of organic and synthetic materials, as well as some metals, can form combustible dust. Combustion or fire is a chemical reaction in which a combustible material combines with an oxidant to release energy. Part of the energy release is used to sustain the explosion by utilizing existing heat or creating a vacuum to consume more oxygen. Within a hazardous environment, there are three elements necessary for a fire or explosion: a combustible material, also known as a fuel, ignition source, either electrical arcing or general heat, and an oxidizer, also known as oxygen. When a fuel, oxidizer, and ignition source are present at the necessary levels, burning or explosion will occur. To reduce the possibility of fire or explosion, one of the key elements needs to be reduced or removed. Another key factor in a fire or explosion are the explosive limits. These are the maximum and minimum concentration needed of a given combustible material to support a fire or explosion. To form an explosive mixture, the hazardous gas must have sufficient concentration levels. The minimum concentration of oxygen to combustible material is known as the lower explosive limit, or LEL. If the concentration is below the LEL, it will not be flammable or have enough flammable material present. The same condition would apply if gas concentration is too rich, meaning it will not ignite because it will not have sufficient oxygen to sustain the fire or explosion. This is known as the upper explosive limit, or UEL. It should be noted that different gases will have different threshold limits. In this example, the LEL of hydrogen is 4%, and the UEL is 75.6%. Therefore, any mixture of hydrogen and air that falls between these limits will have a flammable mixture. In addition to the explosive limits, each hazardous material will have an auto-ignition temperature and a flash point. The flash point is the temperature at which the material will generate sufficient quantity of vapor to form an ignitable mixture. As the liquid is heated and reaches the flash point, auto-ignition could occur. An auto-ignition is the lowest temperature at which a combustible material will spontaneously ignite in a normal atmosphere. In this example, we have the heating of a combustible liquid. Explosive vapors are created as the material reaches the explosive limits, creating the flash point. If the general atmosphere is increased to the auto-ignition temperature, fire or explosion will occur. To simplify the specification of electrical devices into hazardous environments, IEC classification methods utilize auto-ignition, flash point, and explosive limits to place the hazardous materials within groups. The two predominant methods used for classification of hazardous environments are the NEC and IEC standards. IEC and NEC standards both classify the level of risk into three main categories: continuous, occasional, and not normally present. All three categories provide the likelihood of an explosive atmospheric condition within the general environments. Within the IEC standard, the general risk categories are then classified as zones. This reflects the physical material that could provide a potential fire or explosion. For liquids and gases, the area classifications are Zone 0, Zone 1, and Zone 2. By altering the physical material to dust or fibers, the area classification numerical value changes to Zone 20, Zone 21, and Zone 22. Referring back to the necessary requirements for an explosive triangle, we know we need an ignition source, oxygen, gas, and/or dust combustible material in the correct mixture within the atmosphere. In order to specify electrical devices and hazardous locations, we need to identify the general zones within each area. When working with liquids or gas, we locate the most hazardous or flammable location directly above the material. Due to the possibility of the valve leaking at the top of the containment structure, we must classify the area as Zone 1. As we move further away from the possible explosive atmospheric condition, the zone classification would be reduced to Zone 2. By altering the combustible material properties to a solid form, the area classification above the material would be Zone 20. If the dust escapes the same failed valve, the external area around the containment unit would be classified as Zone 21. As we continue to move away from the containment unit and with reduction of category risk, the new classification for the general area would be Zone 22. Now that we know combustible materials, whether liquid, gas, and/or dust, will have different upper and lower explosive limits, and we understand the general heat could be the ignition source, within the IEC standards, the T rating specifies the maximum surface temperature an electrical device will create. As the temperature increases, the associated rating will decrease, meaning less heat will have a higher T rating, while an increase in surface temperature will reduce the T number. As a recap, the IEC standards classify hazardous areas as environments that could contain explosive vapors, gases, and/or dust within the atmosphere. The primary categories provide the risk levels as constant, occasional, and not likely. Since elements have a variety of flammability and the physical properties could be different, IEC standards segment the types of combustible materials into zone classifications. The most hazardous is Zone 0 or Zone 20. By reducing the risk level to have occasional explosive atmospheres, the zone classification is Zone 1 or Zone 21, and further reduction of category risks would change the hazardous classification to Zone 2 or Zone 22. Let's take a look at each method of protection and the general application. To ensure safety in a given situation, equipment is placed in protective level categories. As mentioned before, Category 1 is the highest safety level, making Category 3 the lowest risk and safety level. The general 8 protective methods are flameproof enclosures, sand encapsulation, pressurization, oil encapsulation, general encapsulation, increased safety, intrinsic safety, and non-sparking. The flameproof method is a type of protection where devices that are capable of igniting an explosive atmosphere are built inside an enclosure. This protective method prevents the transmission of the explosion to the external atmosphere surrounding the enclosure. This method of protection would be suitable for applications on power-operated equipment, switchgear, motors, and any equipment that produces an ignition source during normal operation. Sand encapsulation is a type of protection in which the enclosure of the electrical apparatus is filled with a finely granulated material. This ensures electrical arcs occurring within the electrical apparatus will not ignite the surrounding atmosphere. Pressurization is a method of protection by which the entry of a surrounding combustible material is prevented by maintaining a protective gas within the enclosure. This is generally accomplished by creating a higher pressure within the enclosure than the surrounding atmosphere. This protective method would be used for any power-operated equipment. Oil encapsulation is a type of protection in which the electrical apparatus or part of the electrical apparatus are immersed within an oil-based fluid. The general application for this type of protection would be used for switchgear units, circuit breakers, and transformers. Encapsulation is a type of protection in which the device that could ignite an explosive atmosphere are enclosed within a resin. The material used would be resistant to environmental influences, heat, and/or sparking from electrical components. The general application for this protective method would be used for electrical circuit boards, miniature motors, and valves. Increased safety is a type of protection where measures are taken to prevent the possibility of high temperatures and the occurrence of ignition. This method includes the interior and external portions of the electrical apparatus. The general application for this protective method would include connection and distribution boxes, luminaires, measuring instruments, and devices that do not normally produce ignition within operation. Intrinsic safety is a protective method to ensure that the available electrical and thermal energy in the system is always low enough that the ignition of the hazardous atmosphere cannot occur. This is achieved by ensuring that only low voltages and currents enter the hazardous area, as well as all electrical supply and signal wires are protected by safety barriers. The general application for intrinsic safety would be used for measuring and control engineering, data engineering, and low electrical valves. Non-sparking equipment and wiring process is a protective method where apparatuses are designed with low power levels and low stored energy. This ensures that an arc produced during normal functionality of the equipment or as the result of equipment failure has insufficient energy to ignite the hazardous atmosphere. The general application for non-sparking protective methods would be used for motors, lighting, junction boxes, and electrical equipment. All equipment certified for use in hazardous areas must be labeled to show the type and level of protection applied. In this example, we will review a fluorescent light fixture within a hazardous environment. The first identifying mark will reflect the apparatus group by hazardous application. A 1 would indicate usage for coal mines, while a 2 would indicate general industrial environments. The next identifying mark is the category risk level. As mentioned earlier, there are 3 category risk levels that would identify the occurrence of an explosive combustible material. The next mark identifies the type of combustible material within this hazardous environment. The available option would be the letter G for gases or the letter D for dusts. The next mark identifies this fixture as manufactured to meet the European standards. The next letter indicates the type of protective method used. Referring back, the letter D would suggest the electrical device utilizes a flameproof enclosure. The next number and letters will identify the explosive gas group. Remember, the gas group provides the critical information on the combustible material's explosive properties. The final marking provides the maximum surface temperature of the fixture during operation. In summary, hazardous locations could exist in multiple industries. The geographical location will dictate the general method used for classification. The European Standard, or IEC, provides guidance of risk into 3 main categories. These risk levels are then divided into zones and have numerical values that relate to the possibility of explosive gases or dust present within the atmosphere. Because combustible material could have a variety of explosive limits, The method of protection will be important. Nevertheless, all electrical devices placed within hazardous environments will follow the device markings to ensure fire or explosion does not occur.